Thanks, Mac, and thanks for organising the symposium. And I feel rather challenged to be talking on neuromodulation, but I've enjoyed the challenge. Okay. I don't need that. Good. So I'm going to be talking about some of the underlying computational principles, and in particular, how effects that are felt at the level of the individual neuron can influence quite profoundly. Thank you. Large-scale brain dynamics and cognition. So the basic unit of the brain is the neuron. This is an approximation, equipped with its excitable membrane. Glutamate neurotransmitters yield PSPs, postsynaptic potentials, by diffusing across the synapse. So I've got a bit of a tutorial here, and I'm just got to rehearse it through. So I hope if it seems trivial, you give me a bit of latitude anyway. And open some sodium channels and produce this excitatory postsynaptic potential. And over here on Eli's kick-ass neuron is a GABA neurotransmitter opening chloride channels and eliciting an inhibitory postsynaptic potential. So in computational neuroscience, we can model these. Don't worry about the differential equations. The important thing is here, there's an alpha and a beta. The alpha is the characteristic rise time, and the beta is the characteristic decay time of these postsynaptic potentials. And I'll be returning to this in a few minutes. Postsynaptic potentials yield changes in the postsynaptic potential by repeatedly arriving and summing if they haven't decayed. Volleys of these then sum through the dendritic tree down to the cell soma, where they, through the action of voltage-gated ion channels, yield action potentials. And these can be captured by the Hodgkin-Huxley equations, the form of which is not particularly important. This was beautiful work from the 1950s. But the important timescale operator here is this tau, which is the speed of potassium channels rectifying the current. So that's the second important thing here. These yield a step-like likelihood of an action potential centred at something called the threshold potential. That's from this interaction of fast and slow sodium and potassium channels. If we increase the dendritic current, the cell doesn't just fire once, it begins to fire more frequently, and that yields this single neuron response curve. So we've reached the membrane potential, and with increasing current from the postsynaptic potentials, we're heading up here towards an Fmax. Now, the neuron has an upper limit of how fast it can fire because of that tau I spoke about a minute ago, which is the rectifying potassium current. This thing, the slope of this curve, is called the gain, and this is something that we're all going to be talking about today, and that's a single neuron gain. And the higher the gain, the more bang you get for your buck. So you only increase the current a little bit, and you increase the firing rate a lot, and that's something that we'll be coming back to as well. Individual neurons, neutrons. I tell you, I've written this talk in 2 days, fueled by pharmacological doses of Nurofen and pseudoephedrine because of a head cold. So these are buried within ensembles of circuits, which are then embedded in networks, which are then integrated through the connectome. And individual spikes are really too weak to influence behaviour. There are some instances where spike timing makes a difference, but on the whole, because of the noisy nature of spikes, if our cognition really depended on individual spikes, then we'd be dealing with a very ill-defined and high-dimensional stochastic system. So it seems increasingly likely, and Mac will be talking about this, that brain function is based upon population coding, so ensemble activity on low-dimensional manifolds, not the actual spike code. And this activity, population activity, is matched to the apertures of OHBM. So how do we do this? Here's a local neural population, and this yields, for this example, 1,000 neurons, and in this spike raster, each action potential has a little dot. And all of these neurons are obeying this high-dimensional Hodgkin-Huxley equation. But if I take a cross-section through here and do a histogram of the states, under most assumptions, if the ensemble is big enough, these distributions follow something very close to a normal probability distribution. And so, instead of modelling all the individual neurons, we can model the ensemble behaviour just by approximating them with a Gaussian, propagating that forward with a complicated equation called a Fokker-Planck equation. And if we actually predict the future ensemble behaviour, then we've achieved a massive dimension reduction. And this is not an unpopular approach in physics. I trained in physics with Peter Robinson, and it's kind of a mean field approximation is just the thing that you do. And it can be done at many different scales. So we've got a complex neural circuit that can be reduced and modelled by a detailed multi-compartment model like the Human Brain Project. That can be reduced further to spiking neurons, where each neuron is just one single point, and then we can go to the mean field reduction that I just rehearsed. And there's people working at all these scales, and there's some very large simulators being built to do this. This is the mathematical mean field reduction. And don't think if you're just working at the level of an ion channel that you've avoided this, because even the behaviour of an ion channel is a slave to its local mean field. Okay, so here's LI's single neuron with its single neuron response function. Here's this probability distribution of states and parameters, and we do something called a convolution, and we end up with this population response curve, a sigmoid gain function, now for the average rate of firing, not the individual rate of firing, as a function of the average rate, membrane potential. And now we have a neural population gain, and it can be flat. In other words, you can increase the voltage and you won't get any increase in firing rate because of a floor or ceiling effect, or it can be in this sweet spot. And if I take the derivative of this, you can see this derivative of this. This is where you get the sweet spot here. So small changes in V lead large changes in firing rate. And that's important. And so is the width of this curve for reasons that I'll come to. So this is our ensemble equation. We have dendritic filtering on the left, and then we have this neural activation curve. And just about all neural field and neural mass equations of this ensemble sort have these two key ingredients. Okay, so 7 minutes is gone. What about neuromodulation? That's 7 minutes that's left, okay. Okay, so I've gone back to the single neuron here, and now we're introducing this dendrite. These are widespread, non-depolarizing synaptic inputs, typically utilizing monoamine-based neurotransmitters. We're going to hear about cholinergic ones, serotonergic ones in the later talks. So how do these work? One mechanism is that the intracellular mechanisms diffuse up to the postsynaptic dendrite and just increase the number of ligand channels. And that increases the height of these postsynaptic potentials. So it's pretty simple. But there's a mixture of timescales in these ligands. And what if I change the mixture? What if I just upregulate AMPA, which is very fast, and not NMDA? Then there's a systematic shift to the left here because I've increased that alpha that I spoke about before. And this is really important because if the alpha is very narrow, you can see these dendrites are tuned to fast spikes, and they're too fast for the slow spikes. Where if it's broad, they're now tuned to the slow spikes. So this is a temporal filter. And neurotransmitters can filter the frequency for which the neuron is most sensitively tuned. Now, what about this other mechanism of going now into the cell soma and perhaps modifying the nature of these rectifying potassium channels? Then we're simply making this slope here, this single neuron firing response curve, steeper and steeper as that rectifying current gets faster and faster. And another mechanism that Mac taught me about is liberating intracellular calcium and changing the threshold. And that's shifting this curve to the left. So now we're going from the single neuron back to the neural mass. What do these look like? Here's the first mechanism, upregulating ligand-gated channels, not changing the gain function. The second mechanism is shifting the gain potentials to the left, making it a faster system, but once again leaving the gain function alone. The third mechanism is leaving the postsynaptic potentials the same, but shifting this, steepening this gain function, and this is something that Mac will come to. And then the fourth mechanism, this liberation of extracellular calcium, when we do the convolution, it shifts this curve to the left. There's a fifth mechanism, that's a dynamic mechanism. If we're sitting down here at a very low depolarized, hyperpolarized state, we're not near this gain function. Without changing the gain function, if there's balanced excitation inhibition, we get pushed up into a region where there's more bang for your buck. Okay, so that's how we've gone from some candidate pharmacological mechanisms at the individual neuron to the sort of computational dynamic principles of neural masses. In the last 3 or 4 minutes, I'm just going to preempt some work that Johanna will be filling out, and that is taking these masses and coupling them together into larger ensembles. And many of you have probably heard of this approach using connectivity data, either tracing studies in primate or diffusion-based connectomes in human. So here's our ensemble of neural masses. They've all got these gain functions. They're not very excited. Now, if the connectome was just random and I then push this excitation inhibition, you'll see global increase in neural states up these uniform gain functions. You won't see any particular nuance topology arise in this system. I mean, whether it's inactive, active, or very active, it'll more or less just completely mirror the underlying connectome. But we know that the connectome isn't random. It's organised around this enriched club of central nodes called the rich club. So if I just now drive the brain in this state, these highly connected rich nodes are the first to go up here because they're getting input from a lot of other areas. So they're the first to see the gain function, and because they're highly interconnected amongst themselves, and Mac may come back to this, you see an increase in integration. And if you want to see some more nuanced effect on top of that, then you need to activate these other noradrenergic and acetylcholinergic systems and start modifying either the postsynaptic filters or the gain functions. And that's how you can then get, in this computational framework, functional segregation. I finished. So, in conclusion, I was having dinner last night and we had this conversation about when are the machines going to beat us, right? Deep neural networks are coming. Actually, of interest, McCulloch and Pitts kind of developed the first neural networks, and at the heart of these artificial neural networks is exactly this activation function. So how this, either a simple neural network or a deep neural network, all these elements are more or less fixed and static, and then through back propagation, the weights between the units are modified, and the system then learns to identify or classify some subject. And then it goes back to a new state. This is completely unlike humans. Here's my friend Roland Girk, who's a vision neuroscientist. And these gain functions are constantly being modulated by these selective ascending neuromodulatory systems, and it then gives the human brain a much broader dynamic range and a much more nuanced and adaptive way of learning and adapting to environmental challenges. So that's why the machines aren't about to beat us, because they don't have neuromodulation. Okay, you can read more about this in some work that Mac and I recently published and preceding review papers. And I'd like to thank Eli again for the neuron that he did for me the other day, and Mac for organising the symposium. Thank you.